In section 5.3, our objective is to find the inverse of a function and to differentiate an inverse function. So let's start by reviewing what it means for a function to have an inverse, what it means to take the inverse of a function. First of all, the notation of the inverse of f of x is f to the negative 1 of x. That's how we write that f has an inverse. What does it mean to have an inverse or to find the inverse? It means we switch the x and the y. We switch the domain and the range. Some important things to remember about functions that have an inverse: if we call the function g the inverse of f of x, just to simplify our notation a little bit, then two things are really important to remember. One, when we do the composition of the functions, f and its inverse, f of g of x, since we're calling g the inverse of f, it gives x, and composition the other way, g of f of x, it gives x. A second important thing to think about is that when functions are inverses of each other, the graphs of those functions reflect over the line y equals x. Let's take a look at the first example where we are finding the inverse and graphing it, and then we'll come back and talk about some more important things about inverses of functions. Find the inverse. F to the negative 1 of x of f of x equals the square root of x plus 2. So we just said that inverse means switch the x and y. Essentially what this says is y equals the square root of x plus 2. F of x is just another way to say y. So how do we find the inverse? We switch the x and the y. We put x where y was and y where x was. We switch them. Well, we want to be able to graph it, so we're going to solve for y. We also want to be able to write it in this notation, f inverse equals. So solving for y, I need to square both sides. So x squared equals y plus 2. I need to subtract 2, so x squared minus 2 equals y. And then I'm not going to leave it like this. I want to write it in the inverse notation. So my final answer, almost, f inverse, f to the negative 1 of x equals x squared minus 2. However, this is a parabola, and yet this original function is not a sideways parabola. Before we write the complete answer, let's go take a look at the graph. I want first to graph the original function. And we know that that's a square root function whose vertex has been shifted to the left 2 units. So left 2 units, or negative 2 plugged in gives 0. Shift 1 to the right, or 1 unit away from there, and we're up 1 unit. Square root of 1 is 1. Square root of 1, 2, 3, 4 is 2. So that's a quick way to find some points on the graph. I've plotted those points. Now I will connect them with a smooth square root function curve. Okay, let's take a look now at the inverse. So graphing the inverse of this, well, this is the entire parabola that starts down 2 units on the y-axis. Let's color match this here. Down 2 units on the y-axis, and then over 1, up 1, and I do that on both sides. But if I create this whole parabola, visually that is not the inverse of this. Remember we said that graphically the inverse has to reflect over the line y equals x. Well, here is the line y equals x. This is that line that we're talking about, that line of reflection y equals x, that the inverses reflect over. So if I have this whole parabola, that's not the reflection of this green square root function. So I'm not graphing this entire thing. I'm only graphing half of it. Well, remember we talked about earlier in the year, how do we know which half to restrict? Well, if I need to restrict part of the domain, if I'm thinking about what is the domain of this, what can x be or not be, I want to think back to the original function, what's the range of this? what can y be and not be? So the range of our green square root function is everything 0 and up. So y can be everything greater than or equal to 0. This is the range of this function. Again, why did we want the range? Because we need to talk about how are we going to restrict the domain of our inverse function. Switch the y with x, and our domain is x is everything greater than or equal to 0. So I only want the part of the graph that is greater than or equal to 0, this part. And now it's an accurate reflection over the line y equals x. So my entire answer for my inverse function is all of this, including that domain restriction right there. So let's think about some things that this problem tells us. First of all, we said that the inverse could not be a parabola because the original function was not a parabola. Well, what if the original function was a parabola? So it would be not just this top of the square root function, but both parts of the square root function. Well, what would that mean for the inverse of it? Well, the inverse of it then would be a parabola approximately like this. But here's what we're trying to work with. We're trying to work with functions. If our inverse was a parabola, its inverse, or if one of the functions is a parabola, its inverse is a sideways parabola and not a function. And we are really trying here to deal with mostly functions. So if we say that our function has an inverse, then it is going to be a function to start with, and its inverse will be a function. So if I were to start with a right side up parabola, let's say, its inverse, if I say it had an inverse, would be a sideways parabola, right? Reflecting over that line, that diagonal line, y equals x. Yet the inverse is not a function. So since we are only wanting to deal with functions, how do we know that our function will have an inverse or will have an inverse that is a function? Well, how do we know this is a function? It's not when it doesn't pass the vertical line test. Therefore, its inverse is not when it doesn't pass the horizontal line test. When it's just going in one direction and not coming down here in the other direction, then we know we're safe. So thinking about going in different directions, if I have a function that is decreasing and then increasing, I know its inverse will be going in different directions. So it won't have an inverse function. So if I get rid of that other half, so it's only decreasing, then the inverse will only be going in one direction. So what does that tell us about functions and how we know if their inverses will be functions? They should be only going in one direction, decreasing, or I keep the increasing part. So some important things to take note of. In order to have an inverse. First, we say f is or must be 1 to 1. That means for every x value is a y value, and for every y value is one and only one x value. How do we know that? Well, thinking about what we examined earlier, f is only going in one direction. Either f is only increasing or only decreasing on its entire domain. Another way to say that it's only increasing or only decreasing, is to say that the function is strictly monotonic. Nice fast way to say that the function is only increasing or decreasing. And then how do we bring the calculus into that? How do we use the calculus to say that the function is only increasing? F prime is greater than 0. How do we say that the function's decreasing using the calculus? F prime is less than 0 on its domain. Now we can look at some examples where we can use the calculus to help us tell that. Example 2, use the derivative to determine whether the following functions have an inverse. Now maybe you can picture what this looks like graphically and you already know if the function's going to have an inverse. But if it says use the derivative, we have to prove it by showing the derivative. So let's start by taking the derivative. 3x squared plus 12. So remember, our way to use the derivative is to determine, is the function derivative positive or is the function's derivative negative? Always and only one or the other, so that we know if the function's only increasing or decreasing. So if we think about increasing and decreasing, what are our steps? Take the derivative, find the critical numbers, setting the derivative equal to 0, and solving for x. And I see I can't take the square root of -4. X squared won't equal -4, so there are no critical numbers. Now, the way that I could have looked at this is to say, I square an x, I add something to it. This right here can only ever be positive. This can only be greater than 0. It's never going to be less than 0. So I know right away that the derivative exists. Let me write that better. I know right away that f inverse exists because f prime is greater than 0 for all x. Therefore, our function f of x is strictly monotonic, always increasing. So we've justified it, saying that our inverse exists because our derivative is positive all the time. Now, if we weren't able to tell just by looking at that was going to be positive, then we'd go ahead and make our number line. So our number line doesn't have any critical numbers on it, and then I can pick a test value and plug it in. Now, this is kind of a waste of time because if there's no critical numbers, it's never going to be changing derivative, changing sign. So 0 plugged into here is always a positive, therefore we can conclude with that. Let's take a look at B. We have the sine function restricted on 0 to 2 pi, sine of 2x. Let's find the derivative. Now, you might be thinking already, well, sine function goes up, down, up, down, up, down, so probably it's not going to have an inverse, but we're restricted on this domain. So maybe it'll have an inverse on that domain. Plus, it's a double angle function, so we might not be as familiar with that. We take the derivative using the chain rule, 2 cosine of 2x. We find our critical numbers by setting equal to 0. Cosine of 2x equals 0, and the cosine is 0 when we're up at 2 pi. So not 2 pi, pi over 2. So the angle is this part right here when the angle equals pi over 2 or even 3 pi over 2. Dividing by 2, we get pi over 4. If I also said 3 pi over 2, dividing by 2, we'd get 3 pi over 4. We want as many of these as we can in the interval from 0 to 2 pi. Let's go ahead and make our number line. Notice that we have that limited domain. So we're going to start at 0, end at 2 pi, and we'll put pi over 4 on here, and we'll put 3 pi over 4 on here, and there may be more, but let's go ahead and see where this takes us. So these are our x values, and up here will be the sign of our derivative. So we need to pick a test value in these intervals. Before pi over 4, maybe we pick pi over 6. Between pi over 4 and 3 pi over 4, how about pi over 2? Now, instead of plugging it into the derivative and trying to evaluate it, we might have a better time thinking about the unit circle and where the quadrants are and how they're positive or negative, or cosine, how it is positive or negative. So we're still going to plug pi over 6 in here, and that gives us pi over 3 for the angle. So let's think about where is pi over 3. Pi over 3 is about right here. Cosine in this quadrant is positive. So over here, positive, positive cosine function, so positive derivative. Pi over 2 plugged in, 2 times pi over 2 is pi. Cosine of pi, well, pi is out here, and the cosine is negative over here. So this is a negative derivative. Now, remember I said there might be more critical numbers, but let's wait and see. Well, we can stop now because we've seen that our derivative changes sign. Therefore, our function f changes direction, increasing to decreasing. If our goal is simply to determine does the function have an inverse, we've done that here. Because the function is changing directions, it will not have an inverse. So we have to say f inverse does not exist because f prime changes sign on the given interval. We can't just say it changes sign because of course it's going to, but on the given interval, it definitely is. And we can also mention how f is not strictly monotonic, meaning not simply increasing or decreasing on its entire domain. So some good information to back up why we know there is no inverse. Let's look at one more, the natural log function. Now you've got to be careful sometimes on domain restrictions that come with a function. Here there was a domain restriction given. Here the domain restriction we have to remember, anything inside a natural log function must be positive. Therefore, x plus 3 can only be things greater than 0. Solving for x, x can only be greater than negative 3. That means when we make our number line, we start at negative 3 and go up. Now, let's find the derivative. F prime, u prime over u makes 1 over x plus 3, setting it equal to 0. Well, when 1 is in the numerator, it can't equal 0, but the denominator can equal 0. So where does the denominator equal 0? Our only critical number at negative 3. Notice where that critical number is, right here, which means no matter what I pick, there's only going to be one sign for f prime. Let's say we pick 0. Plug 0 in our derivative and we get a positive. That's the only sign it will be. So if f prime is only positive or only negative, the inverse exists. Why? Because f prime is greater than 0 for all x in the domain of our function. And we can say f is strictly monotonic because f is only increasing. There we go.